Hello, my name is Clarissa. I'm a fourth year PhD student at the College of Optical Sciences. I'm going to be bringing it down a little bit closer to Earth now to talk about aerosols. Much like myself, they're very small, but they're very impactful. And they come in a lot of different types. There's smoke, dust, sulfate, sea salt, and they highly influence Earth's atmosphere and climate change and all the stuff that is really relevant today, especially on Earth Day. Okay, so there is currently a lot of uncertainties in quantifying the effects of these aerosols, because as you can imagine, it's a very dynamic problem. They mix, they have different lifetimes, they can exist at different levels of the atmosphere. Anything that can give you uncertainty exists in an aerosol problem. How we kind of see from like a more engineering optical standpoint on how we can contribute to this field is tackling these uncertainties by increasing the synergy between measurements and models. When I talk about measurements, it's almost every remote sensing modality that you could think of, starting at the ground all the way up to space and satellites. Today, I'm going to focus mostly on the models, the algorithm side of things. If you hear me say rate of transfer model, this is what I mean. They have inverse problem and a forward problem, wherever you have the atmospheric scattering observations that can be fed into a rate of transfer algorithm to solve the equations to get your surface and aerosol properties like index of refraction, optical properties, as well as size and mass. Or you could go the other way. If you know your aerosol type, you can start modeling atmospheric scattering observations. Whenever we talk about synergy, some of the ideas that come into play in this field of work is employing now statistics-based algorithms. Traditionally, aerosol algorithms use lookup tables that were provided by previous measurements or for a very specific instrument. Say like under these wavelengths in this modality, this is what the atmosphere looked like at this time. So that's probably what you're getting whenever you get those scattering observations from your new instrument. So a move towards more statistics-based algorithms, so we don't need those lookup tables. We don't need to be dependent on previous measurements. Multi-instrument algorithms, can we use more than one instrument as input into these algorithms? For example, like a LiDAR on the ground and a satellite in space, can I take both of those data products and put them into one algorithm? And then benchmarking algorithms. Can we put an uncertainty on this algorithm and the other one and start comparing the results that we get between instruments? For this work, luckily there is a team at the University of Lille, France, who has spent decades working on tackling exactly those challenges that I just mentioned. They created this open source algorithm called the Generalized Retrieval of Aerosol and Surface Properties. It's completely open source, which is really great, especially for a student, to start learning these techniques. They use common statistical inversion techniques. It's adaptable to different instruments, and you can use multiple instruments as input. So we decided to move forward with my PhD project using this algorithm. But there come some challenges too. So when I first put together our data pipeline, we need to know how to use this algorithm for both the forward problem and the inverse problem. And so this is the general idea of taking atmospheric scattering observations, formatting them, understanding some good model assumptions and convergence criteria, and then using this algorithm. I've also done the simulation work, so taking some known aerosol properties and trying to simulate what an instrument would see. Kind of the focus of this talk is going to be this formatted data products. So generalized algorithms are really great, but you have to know what they expect. What are they trained to do? And that comes with, again, like a lot of challenges of using the generalized algorithm. The main ones that we identified was first data curation. So a lot of data products are very different. I'm in the polarization lab at the Wyant College of Optical Sciences, so we deal with multiple angles, multiple wavelengths, and polarization, which gives you a lot of rich information content, but also can provide a lot of complexity. So I needed to know how to handle all of that, georectify everything. As I just mentioned, polarization, it's essentially a giant geometry problem. So whether you're on the ground or airborne or a satellite, you have to define your coordinate space for all of your data products. And then again, this is a generalized algorithm, so they got to give somewhere. So you have to format your instrument to fit the algorithm rather than having an algorithm built for your instrument. This just, I guess, self-plug that I published this work earlier this year if you want more information, because this talk will definitely not go into all of the specifics. I first tested this data pipeline on Aramispe data products, which is the airborne multi-angle spectral polarimetric imager from NASA JPL. Here are some specifications. The really cool one for us was this 0.5% polarization uncertainty, which is really, really good. Less than 1%, so very accurate. It only has 3 polarization channels. The other ones are simply radiometric. I took data from the FIRE-X-AQ campaign, which was a campaign in 2019 with NASA, NOAA, and JPL to start studying wildfire smoke. So I'm just going to show a little bit of the process that I did with that data. This is an image taken of a fire just in Prescott, Arizona in August 2019 at Nadir, so looking straight down. And I took just this little region given by the orange box, which is about a 5 by 5 pixel region, and took the median of the values for radiometric and polarimetric values at all of these wavelength channels, except the 935, because smoke is basically transparent at that wavelength. And so we didn't have validation data, so I'm not going to show the aerosol results, but a really cool thing that we discovered we could do based on that geometry problem is take, and based on the algorithm's capabilities, is it had 2 reference planes for polarization. And so it has the meridian reference plane, which is your instrument's view direction and the zenith, and then the scattering reference plane, which is the instrument's view direction and the sun vector. And we could essentially benchmark this algorithm against itself and see how the results compared across wavelengths. These different colors are just different wavelengths in radiometric polarization and the 2 polarization quantities, and see how they compared with the exact same input. All we changed was the reference plane, and essentially the errors were really, really low, down to the 1,000th percent. So that shows that the algorithm is working very well, and whenever it's benchmarked against itself. So with that, I just want to acknowledge my funding from NSF, JPL, and shout out to the GRAPS team at University of Lille for helping me a lot with understanding their algorithm and this project. If you want to learn more about the polarization lab, you can scan here, and that's it.
Questions?
Thanks. Really interesting talk. I just had a question about something you said where you have to fit your instrument to the algorithm and not the other way around. I'm just wondering if there's any challenges you've encountered with that or ones you foresee in the future.
With the other way around, or trying to fit your... Yeah, so with currently that's how it's done. Most instruments have their individual algorithm, and that works really well because it's made for that instrument, of course. But whenever you have an entire payload with a bunch of different instruments, then you have two with different results, and a lot of the algorithms are kind of in a black box. So it does cause problems with comparing results to each other and just kind of trusting that algorithm or kind of understanding the one good example is Miser. Initially, it was made to kind of ignore smoke with this initial algorithm. And so whenever it sees smoke now, it gets it really wrong because it was just based on lookup tables before. So there's little problems like that. It has worked really well for a long time. But yeah.